In this question, we're asked to sort this list of numbers using bubble sort, and it's a good idea just to write your numbers on little pieces of paper and keep a track of the pair of numbers that you're comparing. Just bear in mind that what's happening in a CPU is we've got three main components. We've got the cache, we've got the control unit, and we've got the arithmetic logic unit, which can do calculations. Now, one of the calculations instructions that it can deal with is to be able to compare two numbers and to decide which is the biggest. So we can make use of that. And what we're going to do with bubble sort is it's an algorithm that repeatedly steps through the list. It compares adjacent elements that are next to each other. I'm using the word elements because, you know, as well as just numbers, it could be words as well. It could be other things that we're comparing. And if it's in the wrong order, we're going to swap them. Now that's really useful to be able to quote how the bubble sort works. So something along the lines of an algorithm that repeatedly steps through the list, compares adjacent elements and swaps them if they're in the wrong order is a good thing to learn. Okay, let's go through it. We're going to do what we call the first pass. We're going to compare the first two numbers and say, are they in the correct order if we're going from lowest to highest, in other words, in ascending order. They're in the wrong order, we need to swap. Then move along just one, please. That's in the correct order, don't swap. Move along one. That's in the wrong order, swap. That's in the correct order, don't swap. And the last one is in the wrong order, so we can swap. Now we've got a new list of numbers. Let's just write those down. We've got 5, 9, 3, 12, 11 and 17. And that's called the first pass. Right. What's happened is that the last number here, 17, the biggest number will always rise to the top. A bit like a bubble, I suppose, in fizzy water or something, rising to the top. So the 17 is actually done. That's in the correct position. And it means that when we come to do the next pass, I don't need to compare that one because we know it's right. So if you're writing your program efficiently, you want it so that each time it does a pass, it's not going to bother comparing things that we know that's in the right order. Right, let's go through the second pass. 5 and 9, correct order, don't do anything. 9 and 3, we need to swap those. They're in the wrong order. 9 and 12, correct order. 12 and 11, wrong order. And I stop at that point. So I'm doing slightly less calculations, slightly less comparisons. This is called the second pass. 5, 3, 9, 11, 12 and 17 is called the second pass. Just notice that the 12 now will have bubbled to the top. That's in the correct position. So when we come to do the next pass, we don't need to do it. It's a good idea just to try this yourself and see if you can do the third pass. Anyway, let's just have a look at that. We've got 5 and 3 is in the wrong order, so we're going to just move those around. And next one, 5 and 9, fine. 9 and 11, fine. And I wouldn't bother with the rest of them, so that's the third pass. So we have got 3, 5, 9, 11, 12 and 17. Don't fall into the trap of thinking that's finished, all right? 11 is in the correct position. I know when you're looking at it, you can say, oh, it's in the right order. The computer doesn't know that. It might still have to do some swapping. So to finish off, we will have to, if we're writing this algorithm, do it one more time. And in fact, we say compare 3 and 5, don't swap, don't swap, don't swap, don't swap, don't swap. And we write that out again. 3, 5, 9, 11, 12 and 17. The point with that is it's the computer needs to stop the program if there were no swaps. So just get your head around that. If there were no swaps, the only way that can happen if there were no swaps during a pass is if the list of numbers was in order. So we can stop. So I've got that final pass. So the number of passes needed for this one is 4 passes. It is just worth thinking about what a sort of worst case scenario could be with bubble sort, and it would be something like this, where you've got this 3 is going to take a while for it to get back down, and in fact we've got 1, 2, 3, 4, 5, 6. We've got 6 items there, and we would need 6 passes in order to complete the algorithm. So you can see one of the problems with bubble sort is as your numbers get bigger, you've got quite a few calculations to do in the worst case scenario. The good news about bubble sort is if you have sorted the list, you're in good shape. It just stops there. It doesn't carry on. So for lists that don't take too many passes, the algorithm can be really good because it will stop when it gets sorted.